to the video about optical isomers. A while back I made a video about isomers in general. So there's two groups. There's structural isomers, so that's your chain isomers, your functional group isomers, and your position isomers. And then there's another group of your stereoisomers. In that I mainly talked about geometric isomers, your E and Z isomers, but there's also something called optical isomers. So if geometric isomers, so stereoisomers in general are molecules that have the same molecular formula and same functional group and functional group positions with different arrangement of atoms in space. So, I should probably write that down. Alright, as I said before, so stereoisomers are molecules that have the same molecular formula, same functional group and functional group position, but different arrangement of atoms in space, producing a non-superimposable image over one another. So whenever you answer a question, like if you ever get asked what's a stereoisomer, it's very important that you use this word, non-superimposable image. I'm going to explain what that means later on and why that's so important to the definition of this. So there's two types of stereoisomers. You've got your geometric isomers and you've got your optical isomers. So geometric isomers, as you saw in the last video, they produce a non-superimposable image with your E and Z isomers, but they do it through a double bond because double bonds are rigid, so you can't twist them, or you can't make the images the same because of the double bond. The molecule has the same molecular formula, functional group, and functional group position, but the atoms are going to be arranged differently because of the rigidity of the double bond. So expresses So, as I said before, like we already did the Kahn-Ingold pre-log rules. Everything is expressed in that video, but essentially, if you have the molecules that are on the same side are going to be called Zusammen or Z isomers, and if the heavier group is on opposite sides, it'll be an E isomer. So you've got E and Z isomerism, or E and Z isomers, as you call it. Optical isomers is something different, so we're going to get onto today. So it produces two we call optically different isomers. That's due to something called the chiral center. I'll explain what it is just in a second. So So just to clear up quickly about what I meant by the geometric isomers, I already done it in my other video about geometric isomers. I want to fully focus on optical isomers, but I'll just clear this up quickly because I didn't explain it properly. This is right. This should be Z means Zusammen, so that's same, and then opposite. Yeah, okay, cool. That's right. So what I meant by the double bond is rigid. This bond here, these two molecules are different, because one is on the opposite side, where the heavy group's on the opposite side, which is the E isomer, and one is the Z. These can't, it can't be like this. Like these two here can swap. These two compounds, they can't swap around. fuck? Because, so that can't happen because this bond here is really strong and it's really rigid. So in all planes, this will always be, this is all going to be on one plane because of this double bond. And it's the same thing here. So this is always going to be opposite here, and this is always going to be same side here. And that's why these two are geometrically different. Optical isomers are different. I'm going to explain that now. Alright, so it's probably edited here. So optical isomers aren't superimposable. Optical isomers are non-superimposable images of each other. But what is non-superimposable images of one another? So a non-superimposable mirror image is like, it's a mirror image, but they're not completely the same. Like, for example, if I was to use my hands, for example, these fucking crusty hands, move this back. Yeah. If I was to get my hands here, they're mirror images of each other, but they're not, I can't twist my hand so that it becomes a left hand, if that makes any sense. Like, I can't do this, like, they're not the same. Like, they're opposite with one another. So these thumbs here and the rest of my fingers, they're not the same. Like, I can't twist it in such a way that a right hand will become a left hand, if that makes any sense. So they're mirror images of one another, but they will never match up. Like, they can't do this, essentially. Like, so that's pretty much what it is. It's that I can't, you know, I'll show a couple examples of where it is in a molecule, but for a visual representation of it, you know, I could do this, but that's not the same as this left hand being the same as a right hand, if that makes any sense. But I'll try and explain it. So I'll try and explain it better here. So if I go back to here, let's just delete this. Alright, great. So let's make two mirror images here. Let's get a carbon molecule. I'll get two carbon molecules. I don't really care about the molecules itself. I'm just gonna try and make an example here. So the carbon in here. Yeah. And then let's get three colors. Let's get green, red, yellow. And now I'm going to do the same to the other side, but it's going to be a mirror image of it. So we have yellow here, red here. Oh, very weird. Bit of a technical difficulty. Yep, red here. And then we're going to have green here. All right. So if we try to rotate these molecules, if I try to, let's see this molecule on the right here. If I try to rotate the molecule on the right and try to match it onto one to the left, it would never happen. Like, I can't, it's not possible to make this image, so it's not this image, this molecule, the same as this. Because if I do, yeah, I'll move it down here. So if I change this to like a black or something, yeah. So if I redraw these images here, I get the so let's put that there. Oh. keep this as, so we're going to keep the left side as it is. Yeah, okay, just, and then, so yeah, and then put the yellow here. But now I'm gonna rotate the other side. So now it should be, if I try to rotate it, like that. Yeah, so it'd be like this here. Mustn't forget this here. That would be there. Now you see, if you look back at it now, these are not the same image. I tried to rotate this image here to make it into the same side, to try and make these the same image. But as you see here, this image this is coming out of the page, that's going towards the right. These are not the same image. They're not the same molecule. So if I to tick them off, these are the same. That's the same. That's the same. Carbon's the same. But these two are switched around. They're not the same. That's what I mean by they're non-superimposable. So they're mirror images of each other, but they're not the same molecule. They can't match to be one and the same. If they were one and the same, they would be superimposable. All right, we've been talking a lot about chiral centers and how they're used to, and how they completely differentiate optical isomers from geometric isomers in the stereoisomer class. But it's important to know what a chiral center actually is. And a chiral center is so any molecules that have 4 different groups bonded to one carbon atom, and usually form 2 mirror images. And the carbon atom showing the chirality is the chiral center, i.e. the carbon molecule that has the 4 different groups is the chiral center. I'm going to show an example here. Let's get rid of that. So, yeah. Let's use this example. Let's have a cyanide molecule here. So I'm going to have a cyanide molecule, that's one of the groups. And then you have, let's have an oxygen atom here. It's not a straight line, but hydrogen group, so I can just put that there. And then bromine. And let's have a bromine group here. So this is an optical. This compound here will have an optical isomer. The reason being is that it has 4 different groups bonded to one carbon atom. So you usually have, this is just one, as you see here, it's just one example here. But you could have a very large molecule, and as long as that large, anywhere within that large molecule has a group with 4 different side groups to it, that compound will have an optical isomer. So in this case, you might get an exam question asking you where the chiral center is. It'll be 1 mark question. It's always the molecule that has the 4 different groups in it. So we have 2 carbons here. This carbon here and this carbon here. Well, let's see. This is the correct one. The reason why this isn't the correct chiral center because it just has the N and it just has the carbon. So the carbon with everything else in it. Like but it's mainly just the carbon-carbon bond here and just the carbon nitrogen bond there for the cyanide bond. So that's not that's not your chiral center. Then we come down to this carbon here. It has your cyanide group in it, your oxygen group, hydrogen group, and your bromine group. There are 4 different groups. Therefore, that's your chiral center. And you usually represent a chiral center with an asterisk. Well, it's not that big, but just give you a little. So yeah, this is quite, I drew quite big, but you have a bit more space and you can just write it much more smaller than this. So I'll show you why this has a chiral center. So yeah, for the same reason as up here, as the same reason as the previous example, I'll just do this. So when we had this example here, the reason why I said these are opposite molecule, or these are not the same molecule, non-superimposable, because we said that they can't be the same image. You can't rotate them to make this image, to make this molecule into this molecule, as shown by down here. And it's the exact same thing here. I'll have to just do that again. Oh, no problem, I'll just do it again. Alright, so this is an example to show you why these images are not the same, or to show chirality exactly. In the exam, when they tell you to draw these images, and I explain how you draw them, how you get to this, but to explain what the examiner is trying to show you, or what the exam board is really trying to show you, is why these molecules are different. So I've reflected these images. They both have chirality, as we've seen before, 4 different groups. Center of chirality there, or the chiral center there, and these are now flipped. I've done a mirror image of this molecule. So you're gonna think this image is not the same as this, and I'll show you why. If I was to flip this image here, so if I was to do that again, it would be if I was to flip this image, let's do a better image. Let's do it here. So this should be going into the page. This is the flipped image of this image, of the right image. Let's make it. Alright, so as you've seen here, this image is not the same as this image here, and that's why these molecules are not the same. There's no way that you can orient this image to get this image. The top, as you one second. So the top side group, the cyanide group, remains the same. The bromine group remains the same, but the oxygen. This is the oxygen here. Yes, sir. This oxygen is going in the original. Well, this is still the same image, I guess, but in the original, it was going out of the page, and hydrogen was going. Sorry, the oxygen was going into the page. the hydrogen was going out of the page. Now if we flip that image, now the bromine goes onto the other side, and now we're trying to make this image look the same. We're trying to make them look the same. Cyanide group, bromine group are the same, but the hydrogen group is going out of the page. So it's going into the page, and the oxygen group is going out of the page. So see here, these are flipped round. The hydrogen and oxygen are flipped round, so they're not the same molecule. Yeah. And all I'm doing here, is literally a 180 flip. Spinning it 180 degrees. And yeah, as you can clearly see, not the same image. Alright, so now I'm going to explain to you how to actually draw. Because part of the exam, you actually need to know how to draw enantiomers and be able to draw how to express that it's an enantiomer and the two different enantiomers. So I have this example here. So this is a skeletal formula here, but you have these weird lines here. So you either got you got the normal lines. So dashed bonds is like this kind of dashes here. That indicates that the atom is below the plane of the paper. So if I was to, I don't know how to actually. Yeah. So if I was to get this is the carbon, and then this is the bond representing the atom here. If I was to get into the paper, it's showing that in a 3D structure, the bond is like this. It's going outwards, kind of going outwards below, or in this case below the paper, the plane of the paper. And then this would be the standard plane here. The wedged lines indicate that the atom's above the plane of the paper or coming out, so it's kind of going like this, or it's just kind of facing outwards. In this case, it'd be above the plane of the paper, or it's more closer towards you, if that makes any sense. So the whole point of these dashed and wedged lines is just to show 3D orientation. And then the normal lines are just normal lines, so they're in the same plane of the paper. The different optical isomers of in this molecule here is bromohydroxyacetylnitrile, because of bromo. You got your hydroxyl group, and then you got your cyanide group. Pretty obvious why it's named that. Anyway, the different optical isomers of this compound are shown above. You can't, and I said they're non-superimposable, so you can't rotate them. You can't rotate this image in order to make you can't rotate this image in order to make this one. They're not the same molecule. So, drawing enantiomers, you need to be able to draw these enantiomers for the chiral molecules. So, that chiral center there. The chiral center. So, step one, you need to identify the chiral center. So you need to, that's the first thing when you're making these enantiomers. You need to identify which carbon is the chiral center, and that's the one with the 4 different groups on it. So here you got a hydrogen group, hydroxyl group, bromine group, and then your cyanide group. And then so your chiral center is the carbon atom. Actually, I don't need to say that anymore. The molecule above has a chiral center at the carbon atom, which is circled. So I just circled it here. So once you've identified the chiral center, you need to draw the 4 different atoms groups, any order of the chiral center, making sure that you get the 3D orientation, i.e. the wedged lines and because this won't suffice in an exam. You have to show its 3D orientation, i.e. the wedged lines to show it coming above the plane of the paper, and the dashed lines show that it's going below the plane of the paper for some of them. You only really needed to do it for like 2 of them, and that's usually the one that's coming behind, the one that's coming up. So yeah, that would be step 2, which is just drawing the 3D orientation. Step 3 is you need to do the exact same thing. You draw a dotted line to the right of your first enantiomer. So you just draw like a dashed kind of line in the center to show, to the right side of this, your original molecule, and then you do a reflective image of this. So you just do a reflective image of your original molecule, and now you have 2 molecules either side of the dotted line. Make sure to do a dotted line to show that it's a mirror image of it, and that's acceptable in your exam. So once you've drawn your mirror image of this, you've now drawn 2 non-superimposable images, so non-superimposable enantiomers of each other. Right, so also in your exam, they may ask you, because these are enantiomers may be very hard to identify, there's a one way that you can identify, because enantiomers, they still have the same chemical property, same functional group, same pretty much the same structure and the same functional group position. However, the only thing is that different arrangement of atoms in space. So it's very hard to differentiate your 2 enantiomers. One way of doing it is using plane polarized light. So plane polarized light is pretty much the only way of you identifying which enantiomer that you have. Optical isomers are called optical due to how they interact with plane polarized light. So, light has a property called polarization. If light is plane polarized, this means that all the light waves have the same equal polarization. So this can be thought of as an edge of a piece of paper held in the air. It could be slightly horizontal, vertical, or anything in between. Like light is the same, it's in the same plane, is what they're trying to say. Let's say they all have the same polarizing effects on each plane. That's pretty much why plane polarized light is able to essentially polarize these molecules and cause them to rotate. Yeah, so enantiomers, because they're if you get the one specific enantiomer, enantiomers will rotate the plane polarized light in either anti-clockwise or clockwise. So if you have your sinister, you have 2 types of enantiomers: sinister enantiomer and rectum enantiomer, or S and R. Sinister just means left, and R means just right enantiomer. So if you have an S enantiomer, it means that it's reflected, rotated. Sorry, the S enantiomer has caused the plane polarized light to be rotated to the left. If you have R enantiomer, it means it's caused your R. You can tell that you have an R enantiomer if the plane polarized light has been rotated to the right. And that's pretty much all. That's pretty much how you're able to tell. You just need to see where the plane polarized light has been rotated, in which direction. And because they're the same, they'll be done in equal angles. So if one rotates something 23 degrees to the left, it will degree. So if you have your left, your sinister enantiomer or S enantiomer, it will say it rotates it 25 degrees to the left. It will the R enantiomer will rotate it 25 degrees to the right, and that's also one way of saying that those enantiomers they are enantiomers of one another. It's one way you can identify as well. However, one way that your enantiomer will not be represented, or you can't really tell if you have an enantiomer, is when you have both of your enantiomers in the same beaker. So if you have both your enantiomers in the same beaker, you produce something called a racemate mixture, and in which you have essentially 2 racemates. Because both of the enantiomers are mixed together, the plane polarized light can't be reflected in, or can't be rotated in a certain direction, and you won't be able to tell what you have. The test won't work essentially. So an equal mixture of enantiomers is called racemate. Racemates are optically inactive due to the different optical activities of each enantiomer exactly cancelling each other out. And that's called a racemate mixture. And that's it pretty much. Hope this video actually helped. Probably didn't.